All right, so let's do this. We're going to start by talking about something that's called an empirical formula. All right, and we'll relate this back to our main focus of this particular chapter, which is the mole, here in a minute. All right, for right now, we're going to lay down some definitions. We've discussed chemical formulas before. These are simply a summary of the number of atoms or ions of each element in a compound. Right, so for example, these are what we've been looking at. An example would be something like CO2 or NaCl. Right, these chemical formulas. Okay, so then an empirical formula is a fully reduced chemical formula. Okay, so what do I mean by that? Let's do an example. Glucose has the chemical formula C6H12O6. Is this an ionic or a covalent compound? Covalent with all those nonmetals, right? So we can even more specifically call it a molecular formula, but we'll call it a chemical formula to be consistent. Okay? So then its empirical formula is what I would get if I fully reduced this chemical formula. I pulled out any common factors that all of those subscripts share. 6, 12, 6, they all share what common factor? 6. So if I pull a 6 out from each one of those, I get CH2O. Right, so my empirical formula is when I take my chemical formula and I just fully reduce it. I pull out any common factors that those subscripts share. Okay. Fun fact, glucose is a sugar. It's kind of a central sugar in our metabolism. Sugars are also known as carbohydrates because they all share this empirical formula here with carbon and water. Carbohydrate, that's where the name comes from. All right, cool. So importantly, for ionic compounds, what did we say about the chemical formulas of our ionic compounds? They always have to be fully reduced. So for an ionic compound, its chemical formula is also its empirical formula. They have to be one and the same, just by the rules that we laid down, right? So for ionic compounds, your chemical formula equals your empirical formula. But as we just saw, for our covalent compounds, that's not necessarily the case. All right, their chemical formula does not have to equal their empirical formula. Because for covalent compounds, we said those subscripts could be any number. There wasn't any rule like there was for our ionic compounds. Okay, so why do we care, right? Like, what is this empirical formula business doing for us? So it turns out that there is an instrument called a mass spectrometer. All right. You will talk way more in depth about this particular instrument in organic chemistry in terms of how it works and all that jazz. Okay, we actually have one in the back that you would utilize in your organic chemistry course. For our purposes, we're just going to make a note that this instrument allows us to determine the empirical formula of a compound. Okay. Likewise, we can also use this to determine the molar mass. Okay, and so that's what we're going to work on here. We're going to look at some of this mass spec data, and we're going to use it to figure out what the empirical formula of a compound is. Okay? And just like from a historical perspective, for a very long time, figuring out what stuff was made of was super freaking difficult, right? I mean, you think back to like the 1800s, they didn't just have a little machine they could put a sample in that told them what they were looking at, right? So the development of something like this is a huge win in chemistry that allows us to sort of figure out what everything is made of. All right, so let's take a look at what some of that data might look like here, what that information would be. Okay, so we have an unknown sample. What we do know is that that unknown sample contains 3.943 grams of carbon and 21.06 grams of sulfur. Those are the only two elements in this compound here. Okay, so what is the empirical formula of our unknown here? Okay, so this is the type of data that a mass spec would tell you. It would tell you your amount of each element that you have in terms of the mass of that element. All right, cool. So step one, now we're going to tie in what we learned how to do last class, talking about molar masses. Everybody's going to take a second and they're going to convert grams of carbon to moles of carbon and grams of sulfur to moles of sulfur. All right, awesome. There's a lot of jingle jangling, right? Because everybody knows that in order to do this, where are you going to have to look? Periodic table. Got to use those molar masses from our periodic table. Okay, and when I convert, am I going to be multiplying or dividing by that molar mass? I need grams on the bottom and moles on the top for my units to work out, so I'm going to divide by that molar mass. Okay, cool. So first step, we had to convert grams of carbon to moles of carbon. I did that by dividing by the molar mass on the periodic table, the 12.0107. I got 0.328 and some change. One of the nice things about these empirical formula problems is we actually don't really have to worry about sig figs. Because let's think of this. If we're trying to determine the empirical formula here, our final answer isn't going to be some mathematical calculation with decimal points and everything like that. It's going to be the formula of our compound here. C something S something, right? And this is what we're trying to figure out here, is just how many carbons and how many sulfurs there are in this compound. Okay? Remember, we used these subscripts to create those mole ratio last time in last class. We would have said that, for example, there's X moles of carbon in 1 mole of this compound. Okay? So believe it or not, hidden inside these decimal numbers that we have here are those ratios, that X and Y, how many carbon atoms there are for every number of sulfur atoms. But it's really hard to tell in these numbers here because they're just big, ugly decimal point numbers. And what do we need in our formulas? We need whole numbers, right? Counting numbers, 1, 2, 3, 4, 5. We're not allowed to have decimals in our chemical formulas. So there's a way that we can turn these numbers here that are ugly into something that will let us see a little bit more easily what that ratio is. All right, so what we're going to do now is we're going to divide each number of moles by whatever quantity is smaller. Meaning I'm going to compare those two answers, the 0.32 and the 0.65, and I'm going to say which one is smaller. 0.3 is smaller than 0.6. So what I'm going to do is I'm going to take these numbers. I took a bunch of decimals, but again, I'm not really worried about sig figs here. And I'm going to divide both of them by that 0.328 whatever value. Okay, I can do anything I want to these numbers as long as I do it to both of them. It won't change that ratio of carbon atoms to sulfur atoms. Right, so I'm going to divide by both of them by that smaller of the two numbers. So again, in my first calculation, I'm keeping track of carbons. My second one, I'm keeping track of sulfurs. Okay, so why do we do this? I said that this was just this trick, this little mathematical trick that will help us see more easily what those whole numbers should be in our empirical formula. All right, so why is that? Well, if I take any number and divide it by itself, what am I going to get? 1. So boom, at least one of them now is a nice whole number. Okay, so this little trick again will help us see these whole numbers. If I take my 0.6 whatever and divide it by my 0.3 whatever, I just copied my numbers to from my calculator to be as exact as I can be. I get 2.0005, which is really close to what whole number? 2. So this tells me that I have twice as many moles of sulfur as I have moles of carbon in this compound. So my chemical formula then should just be CS2. That's my final answer. Let me choose a better color. Right? In this sample, I had 0.32 moles of carbon and 0.65 moles of sulfur. That is a 1:2 ratio of carbon to sulfur. And it's really hard to see that when you're looking at these decimal numbers here. So we have a trick that's going to make it easier to see what that ratio is. And again, that's to take each of these quantities and divide by whichever number is smaller. That allowed us to really easily see that there's a 1:2 ratio of moles carbon to moles sulfur in this compound. All right, again, allowing us to determine our empirical formula. Cool, let's play this game again. Let's do another example. So now we have an unknown iron oxide. All right, and it is going to be 69.94% iron and 30.06% oxygen by mass. I want to know what is, in this case I can even say my chemical formula because it's an ionic compound. Right, same as the empirical formula. Okay? So this one looks a little bit different. The very first step is a little bit different than what we did last time, but it's actually super straightforward here. First thing we're going to do is we're going to simply assume we have 100 grams of our unknown. And you could assume that you had any number of grams, but if we assume 100, it's going to make our lives a lot easier mathematically speaking. Okay? So why is that? Well, if I have a 69.94% iron sample, and I have 100 grams of that sample, how many grams of iron do I have? 69.94 grams. And likewise, if I have 30.06% oxygen in this sample, and it's 100 grams, that's the same as having 30.06 grams of oxygen. And now we're just back to our regularly scheduled programming here. Step 2, everybody's going to take a second and convert grams to moles. And then you're going to do our divide by smaller trick. so if I take my grams of iron and divide it by the molar mass of iron, I get the 1.25 moles of iron. If I take my 30.06 grams of oxygen divided by the molar mass, I get 1.87. All right, and again, my goal here is to find the chemical formula, FXOY. And hidden in those numbers is that mole ratio. All right, but it's very hard to see because these are ugly numbers with a lot of decimal places. So again, we're going to do our trick. I'm going to divide moles of iron by that smaller number. So let's just keep track. This is Fe, this is O. All right, the smaller value is that 1.25 number. Okay, and again, we do this trick because that will guarantee we get one whole number out of the deal for iron. Okay, but now for oxygen, we get 1.500. And this is too far from a whole number for us to just round it up. All right, 1.5 is right in the middle. That's about as far away from a whole number as you can possibly get. Okay, and we're not just going to round these whole things. In general, we will be plus or minus 0.01 from a whole number. Okay, so now it's a little easier to see what this ratio is, but we're still not there yet. Okay, so we have a trick that we're going to use, another trick. Maybe you can see what it should be here, because it's 1.5. If we double it, we get a whole number, all right? But let's say that we couldn't see. How are we going to do this? Okay, what you do is you just take both of them and you start multiplying them by increasing whole numbers. Take both of them and double it. If that doesn't work, take both of them and triple it. Just keep going until you have two whole numbers, okay? In this case, once I double it, I would get a 2 for my number of irons and a 3.00 something something for my number of oxygens. So my ratio here for my chemical formula is 2 irons and 3 oxygens. All right, so my final answer here, don't have to do that step, it's just Fe2O3. All right, cool. So now, just to be a pain in the butt and get us practicing, because we got our first exam next week, I want everybody to take a second and name our iron oxide. What is the proper name of this molecule? Okay, so first of all, looking at this formula, we got to ask ourselves, is it ionic or covalent? Ionic. We got a metal in there. That's definitely going to be an ionic compound. And then is iron type 1 or type 2? Type 2. So now we need the Roman numerals in there. That's what makes this one kind of a pain in the butt. Okay? We got to be able to find what the charge on that iron ion is. All right, so what we know is that we got 2 of them. We don't know the charge of those 2. But what we do know is the charge on each of these 3 oxygen ions in my formula. When I add those all up, I get a total amount of minus charge of what? Minus 6. And again, the sum of your charges have to be 0. So that means I have to have a net charge of +6 on the iron side. But I don't just have one iron ion, I have two of them. And together they sum up to be that 6. So each one must have a charge of 3. 3 plus 3 is 6. All right, so the proper name for this thing, including that type 1 ion, would be iron 3 oxide. Right? No dyes or tries or whatever because it's not a covalent compound. And then since it's type 2, I got to do this work backwards deal and figure out what the charge is going to be on that iron ion. Okay. So the last thing we're going to do with this here, we're going to start out for the sake of simplicity here with this same one, which we already determined the empirical formula for. And now we're going to do something extra to it. Okay, now we're going to take this same sample. Okay, so first of all, let me just say, this is the one that we figured out was CS2. That was our empirical formula. Okay, we're going to put this thing back in our mass spectrometer. We're going to change our settings a little bit, and now it's going to tell us that the molar mass of this compound is 228.4281. If it's a molar mass, what are my units? Grams per mole. And from here, we can say what is the molecular formula. So given our empirical formula, and now we're given this additional piece of information, the molar mass of this compound. From here, we can actually determine what the molecular formula is, right? Not the fully reduced empirical formula, but our molecular formula. Okay? So, since this is a covalent compound, its empirical formula doesn't have to be the same as its molecular formula, but it could be, right? Carbon dioxide is an example of a covalent compound. Its empirical formula is the same as its chemical formula. So it's not guaranteed that it's not. So step one, let's just calculate the molar mass of our empirical formula. And if it matches, we're done. All right, best case scenario. So everybody take a second. We need to calculate the molar mass of CS2. Okay, so we do that, 1 carbon and 2 sulfurs. That's a molar mass of 76.1427. Again, molar masses are grams per mole. So do we have a match? No. All right, crap. So wasn't that easy. So what are we going to do here? Okay, well remember, our possible molecular formula has to reduce to our empirical formula here. Right? So the 1 to 2 ratio of carbons and sulfurs is locked in. So that means that if I'm going to say that I have 2 carbons, how many sulfurs must I have? 4. And if I'm going to say I have 3 carbons, how many sulfurs must I have? 6. If I have 4 carbons, I got to have 8 sulfurs, right? That 1-to-2 ratio has to stay there. Okay? So now I could go back to my periodic table and I could calculate the molar mass of all these different compounds. But importantly, the molar mass of C2S4 is just going to be twice the molar mass of my empirical formula, right? So just 2 times the value that I got before. Now I just got twice as many carbons and twice as many sulfurs as when I calculated it the first time. Likewise, if I had my C3S6 formula, that would be just 3 times the 76 to get my molar mass. 4 times the 76 to get my molar mass, right? So I could just play this game where I sort of guess and checked, all right? There's another way that we could get this number right here, that whole number. Exactly, right? Absolutely. So what I can do is we're going to take the molar mass of our chemical formula and divide it by the molar mass of our empirical formula. That would give me that whole number n. Right? By n, I mean these whole numbers that I took and multiplied by my molar mass to get my chemical formula, my chemical molar mass, rather. So then for this particular problem, it was that 228.4281 will be good, grams per mole, divided by my empirical formula's molar mass, my 76.1427 grams per mole. Punch that into my calculator, and I get that whole number 3. Okay? So then, at the end of the day, I want everybody to take a second and give me the chemical formula for this compound here. What the heck does that 3 mean? Okay? So, to be clear, that 3 tells me that my empirical formula was 3, rather my chemical formula was 3 times that of the molar mass of my empirical formula, corresponding to taking that empirical formula and multiplying each of those subscripts by 3. Right? I took the 1 from my empirical formula, multiplied it by 3, took the 2, multiplied it by 3. So now I get my final answer here. My chemical formula is C3S6. Okay, so given our first problem here, we had this mass composition data. We used that to get the empirical formula of our compound. Once we had that, if we're also given the molar mass of our compound, we can determine the molecular formula. And again, by taking the molar mass of our chemical divided by the molar mass of our empirical, we get this whole number n that we multiply our empirical formula by, giving us our chemical formula. Cool. All right. So now we're going to switch gears a little bit and start talking about actual chemistry here, actual chemical reactions. And so we're going to start by introducing what we call the chemical equation. Okay, so we're going to look at a sample chemical equation and then kind of pick it apart. H2CO3 is a molecule called carbonic acid. Carbonic acid will decompose into water and carbon dioxide. Okay? One of the most important things that I want you to remember about chemical reactions is like How did you know this? You didn't know this, right? I told you this. This isn't something that you're expected to be able to just pull out of thin air and already know, okay? We're going to talk about a lot of chemical reactions. You're not just supposed to know that those happen, not yet at least. There will be a time where we introduce types of chemical reactions, and you should be able to predict what those products are, draw these chemical equations. For right now, you're just going to trust me that this reaction happens. We take this thing, it becomes this thing, okay? So that's kind of, I remember in chemistry being like, well, how the heck did they get that? Am I supposed to just know every reaction ever? Like, not at all. That's not what where we're at here. You're just going to trust me, okay? Cool. So this thing right here is what we call a chemical equation. That's this whole thing. We have this little arrow separating these two halves. On the left-hand side, this is what we call our reactants. And on the right-hand side, this is what we call our products. Okay, and then we say in a chemical reaction, our reactants get converted into products. Right? So if you have H2CO3, it will become water and carbon dioxide. Okay? This is a chemical reaction that happens. All right? And all chemical reactions are about breaking bonds, breaking and creating new bonds. So breaking bonds and creating new bonds. Right, so on my reactant side, the carbon, the 3 oxygens and the 2 hydrogens, they're all bound together in one molecule. And then we take this thing and we rearrange who's bonded to who. And now we have 2 new molecules, carbon dioxide and water. Okay? And that's all a chemical reaction does. You're breaking and making new bonds. That's what a chemical reaction is. All right? So, because of this, there's a very important concept that sort of guides our understanding of chemical reactions. And that is called the conservation of matter. And the important thing that we keep in mind is that matter cannot be created or destroyed. Okay, so in this chemical reaction, it's not like all of a sudden 2 new hydrogens and an oxygen atom just appeared out of thin air, right? We didn't just make something disappear and then something reappear magically. We've just reshuffled who was bonded to who. We have those same hydrogen atoms, carbon atoms, and oxygen atoms. It's just on the reactant side, they were packaged into one molecule. And then we rearranged who was bound to who, and now we have these 2 new ones. But nowhere in that process did I lose any atoms or make any new ones up, right? Matter cannot be created or destroyed. Okay? So from this stems a very important mass composition. So let's just say we have the same number of atoms on our reactant side as our product side. Okay, and since I have the same number of atoms, and those atoms all have their set masses as determined on the periodic table here, Saying I have the same number of atoms on both sides is the same thing as saying I have the same mass on both sides. So same mass of my reactants as the mass of my products. Let's specify specifically. Same mass of reactants that actually react as the mass of products formed. All right, cool. So, given this sample equation here, let's see if we can use this conservation of matter principle. Okay. We're going to do this reaction, and we're going to collect 18 grams of H2O and 44 grams of carbon dioxide. And I want to know what is the mass of that carbonic acid that reacted. All right, well, if I had 18 grams of water and 44 grams of carbon dioxide, that means that the total mass of product that I obtained was 62? Yes, okay. 62 grams, right? So where did that 62 grams of matter come from? Well, it didn't just come from thin air. That means that I had 62 grams of my carbonic acid that reacted, right? All of that carbonic acid, those hydrogen atoms and oxygen atoms and carbon atoms, they're still accounted for. They're still there, okay? So I just simply had 62 grams of that H2CO3 based on my conservation of matter principle. Okay? Also, something that may not be all that surprising, but in the history of chemistry was a big deal. Man, for a real long time, they thought stuff was just magically appearing. Then it's like, oh crap, you can actually keep track of all of this stuff. All right, cool. So then that takes us into what's called balancing our chemical equations. This is a skill that we're really going to have in order to talk about chemical reactions. In the previous example, I gave us one that was already balanced, and so it was sort of ready to go for us to use for that example. That's not always going to be the case here, okay? So let's take a look at one reaction, CH4 plus O2. These combine to give you carbon dioxide and water. All right, and I'm going to draw these sort of molecules here. Draw them out so we can get a better sense of what I'm talking about. So here we got our methane, C with 4 little H's around it. This oxygen molecule is O2, meaning there are 2 oxygen atoms. And this is going to get converted to carbon dioxide. So now I'm going to take my carbon atom, 2 oxygens on it. Okay, and why did I draw them like this? You're just going to trust me on this for now. This isn't something that I'd expect you to be able to do. We will talk about how we put these structures together, but we're not quite there yet. Okay, what I want to show is that as written, we have a conservation of matter violation here. All right, if I'm going to color these in to make them a little bit easier to see, I have 1 carbon atom on my reactant side and 1 on my product side. That's cool. But I have 4 hydrogens on my reactant side. And I have only 2 on my product side. Likewise, I have 2 oxygens on my reactant side, but 3 on my product side. Okay? And importantly, these oxygens can't just have disappeared into thin air or reappeared out of nowhere. Same with our hydrogens, right? That would violate our conservation of matter rule. So the reason why that this violates our rule is because this chemical equation is not balanced. All right, so that's what we're going to do. We're going to balance this chemical equation. So step 1 when you're balancing a chemical equation, very important. You're not going to touch those chemical formulas at all. All right, do not touch your chemical formulas. You can't just solve your problem by saying, all right, let's make this O3 then. No, that is not the same reaction. That's not what we were talking about. You've just changed that molecule. You're not allowed to do that. Okay? What we're going to do is instead we're going to update the coefficients in front of each chemical formula. All right, what do I mean by that? Well, we have not seen these yet, but out front of each of these chemical formulas is what's called a coefficient. A number telling you how many of those molecules are involved in that chemical reaction. And when there's nothing written there, we just assume that there's 1, right? We fill in with our mind's eye a 1, just like in our chemical formula. I implied have a 1 here for my number of carbons. We just leave off that 1. Same thing in our chemical equations. All right, but we can update that coefficient in order to balance our chemical equations. Okay, so again, we said that our hydrogens were unbalanced. If I look, I have 4 on this side, but a total of 2 on this side. Okay, so what I'm going to do is I'm going to balance my chemical equation by putting a coefficient of 2 out front of the water. Now that's saying that I have 2 water molecules that participate in this, or rather that are products of this reaction. So when I do that, I can update my total here. Now I don't have 2 hydrogens, but 4. Is everything okay? No. What's wrong here? My oxygens, I have 2 on this side, but a total of 4 on my product side. So how can I fix that? I'm going to update my coefficient out front of that O2 molecule with a 2. Boom. So again, kind of visually, doubling, meaning I have 2 oxygen molecules participating in this reaction. And now I have a balanced chemical equation. Importantly, by a balanced chemical equation, I mean one that is not going to violate my conservation of matter rules. All right, so this is going to be the name of the game here. I'm going to give you an unbalanced chemical equation, and you're going to balance it for me. All right? Sodium and chlorine gas will react to form sodium chloride. Okay? So step one, we're going to make this little table underneath our chemical equation where we keep track of the number of each element. In this reaction, it's a sodium and a chlorine. And we're going to total up the number of sodiums that we see on the reactant side and the number of chlorines we see on the reactant side, and then do the same thing for the product side. How many sodiums were there on the reactant side? Just one. And how many chlorines? Two. It's Cl2 in that formula, so there are two. And on my product side, my formula NaCl tells me there's just one of each. Okay, so how do we balance chemical equations? One of the things that makes balancing chemical equations a little bit tricky is there's not really like a one approach that works for all of them. It's really a guess and check kind of situation. You're going to find something that's not working, you're going to adjust its coefficient, and then you're going to have to sort of maybe jump back and adjust some other ones. All right, so in this case here, if I balance my chlorines, because that's what's unbalanced, I can put a 2 out front, but that doesn't just update the number of chlorines I have, it also changes the number of sodiums I have. If I have 2 sodium chlorides, that means 2 sodiums and 2 chlorides. So my sodiums were balanced, and now I just threw them out of balance, so now I'm going to jump back to my other side and balance those out. And how do I know that I'm done? Because everything matches on both sides of my chemical equation. All right, so it's kind of a guess and check. You just got to bounce back and forth, find the problem area, fix it, see what happens. All right, cool. Let's do another one here. Aluminum oxide will decompose into aluminum and oxygen gas, O2. All right, so when I total everything up here, I have 2 aluminums on my product side and only, my reactant side and only 1 on my product side, and 3 oxygens on my reactant side and 2 on my product side. All right, so I'm just gonna kind of go down the line here. Let's fix this aluminum situation. Put a 2 out front. Wonderful, now those match. My oxygen situation, though, is a little bit trickier because you can't turn a 2 into a 3. right? So instead, what we have to do is turn them both into what's called their least common multiple. Right? By that I mean I'm going to take my number of oxygens on my product side and multiply it by 3 to give me a total of 6. And I'm going to do the same thing on my reactant side, but now I'm going to multiply that 3 by a 2 to give me 6. All right? The least common multiple of 2 and 3 is 6. I got to turn them both into that least common multiple. The problem is when I do that, what did I just do to my number of aluminums? Now I got 4 on this side. So now I got to go back and rebalance my aluminums. Boom. Okay? So again, a guess and check sort of situation. Just make sure that at the end of the day, all right, now I got 4 aluminums on each side and 6 oxygens. Cool. All right, one more thing we're going to put in our notes about balancing chemical equations that's really important is these coefficients must be fully reduced. Okay, so what do I mean by that? If I had instead tried to say that my balanced chemical equation here was 4 aluminum oxides, which would give me 8 aluminums and 6 oxygens. Well, if you went down the line, you would see that, yeah, you have 8 aluminums on both sides and 12 oxygens on both sides. The problem is that 4, 8, and 6 all share a common factor. That common factor is 2, right? And so this is not a fully reduced set of coefficients here. You have to take out any common factors, just like we were talking about with our empirical formulas and molecular formulas, all right? A proper balanced chemical equation, those coefficients do not share any common factors. So when you get done balancing, one of the double checks you want to do is to just look at your coefficients and make sure that you can't divide them all by 2, for example, right? So again, coefficients cannot have any common factors. Okay, cool, let's do 2 more here. And I'm just going to kind of give you a helpful hint before you get started, all right? So first of all, yeah, everybody take a second to copy these down. I'm going to give you some time to balance them, but before you get started, I'm going to give you like a little bit of a hint onto how you should approach each one. Okay, so for the first one, we have this polyatomic ion. What's the NH4 ion? Ammonium. So we have this ammonium ion there, all right? We see it on both sides of my chemical equation, NH4, NH4, right? So we could break this up and we could count individual nitrogen atoms and individual hydrogen atoms, but we're making way more work for ourselves than we need to do, because this ammonium ion is on both sides of this chemical equation. It doesn't break up at all. So instead of keeping track of nitrogens and hydrogens individually, keep track of ammonium ions, of NH4. So for polyatomic ions, do not break up if they're on both sides. Right, if it was NH4 on one side and on the other side the nitrogen was by itself and the hydrogens were by itself, that'd be a different story. But here it appears on both sides, so let's just keep track of ammonium ions. Okay, as well as, of course, all the other elements in this compound. You're going to do the same thing for iron, for sulfur, and for chlorine. Right, but again, don't break it up into individual N's and H's. Okay, so then in my next one here, what makes this one tricky is that there are so many oxygens. And what do I mean by that? I mean both of my products contain an oxygen atom. So as soon as I change the coefficient on one of them, it changes the total for that side, right? So that means balancing my oxygens is going to be a little bit of a pain in the butt. So if we have so many of one particular element, save it for the end. Save oxygen for last. Balance your carbons first. Balance your hydrogens first. Then go back and balance your oxygens, and your life will be a lot easier. Okay? Cool. All right. So yeah, everybody take a few minutes, see if you can't balance these, and then we'll do them together. right, let's do this. So, starting it off, I have 2 ammoniums on my reactant side, but only 1 on my products. So I'm going to update that. Boom. Now I got to update my chlorines too. Okay. I'm just going to go down the line. So then I look at my irons. I have 2 on my products, but only 1 on my reactants. So I'll update that. Now I have a total of 6 chlorines on that product side. Okay, so now I have to, again, just going down the line, I'm going to change my coefficient. Now to a 6. 6 chlorines and 6 ammoniums. And lastly, I can either go back to the sulfurs or the ammoniums, and I will see that I need to put a 3 out front of my ammonium sulfide. That'll change that to 6 on the reactant side for ammonium and 3 for sulfur. So 2, 3, 1, 6 should be our coefficients here for this balanced chemical equation. Okay, again, this one we said there are so many oxygens. We got oxygen all over the place, so we're going to save it till the end. So that means we're going to focus first on our carbons and our hydrogens. Okay, I'll first balance my CO2. And then I'm going to need 4 waters to make a total of 8 hydrogens. And now that those are balanced, now I'll go to my oxygens. I have 2 on the reactant side. And now total, how many do I have on my product side? Yeah, so I have a total of 8 over here and 4 over here for 12. So I can balance that out by putting a 6 in front of my oxygen, my O2. That will give me 12 on that side as well. So now everything's all balanced. So our coefficients here should be 1, 6, 4, and 4. Cool? Cool. All right. With regard to